Hey guys, welcome back. It's been a bit. Um, been a little busy, but it's all good. Coming into the last two quizzes, I believe. Carbohydrates on this one, and then I think all we have left in the course is carb acids and amino acids. So we're actually getting really close to the end here. So keep up the hard work. Don't lose faith. Almost in about 2 weeks, you guys are finish probably one of the most impactful classes in your class. Necessarily not necessarily the one that impacts your career, but the one that kind of impacted you. And wow, this classes can be a little hard. So how can I learn to work through this hardship? Cool. All right. So we're going to start biomolecules, starting on carbohydrates. Get right into it. I'll try to keep this below hour and a half. So I'm watching the timer like a hawk. Really want this to be very quick. I also made that other video a long time ago. I made it for the 118C class on how to cyclize and some nomenclature stuff and all that. So I'll go very briefly through that stuff today, so we can get through that really fast. Mainly going to spend time on the reactions though. The video is like 20 minutes though, so it's not too long. So it's not like I'm asking you to add another hour on top of this. It's just 20 minutes. So it shouldn't be too bad. So I'll try to keep this under an hour and a half. So yeah, with that being said, let's just get right into it. Carbohydrates, I mean, as the name suggests, it's hydrates of carbon. I mean, these are also sugars too. That's probably what everyone knows this by, sugars. Right? I know it by sugars too. But they're hydrates of carbon. Follow the formula CnH2OM. Because you are just hydrating, you're putting water into an organic structure. Okay, so what does that look like? Usually the build that we'll see is something like this. So just draw a really, small one. Actually, let's draw a larger one. Okay. Just to kind of show how complex it is, because 1, 2, 3, 4, 5. Oh, actually, it can be even more carbon. 1, 2, 3, 4, 5, 6. There we go. Okay. Okay. So this is a typical carbohydrate, hydrate of carbon. And so kind of three elements that should pop out to you guys, right? There usually is some kind of carbonyl, like a ketone or an aldehyde. We have these secondary alcohols littered through the middle of the molecule. And then right at the end, we have this primary alcohol. So primary alcohol, secondary alcohol, ketone, aldehyde. Okay, this is usually the generic build of a sugar. Now, this is kind of a complex sugar. If I wanted to kind of, condense this into a smaller one, I guess I could, right? If I wanted to have all three of these elements in the smallest possible sugar, right? That would look something like this. It would be this here. So this sugar we'll talk quite a bit about in a second, but this is glyceraldehyde. And if you ask a professor, if you ask most OChem people, they will probably tell you that this is the simplest sugar. And I would agree that this is the simplest natural sugar, but we can get even simpler, right? We could even shave off a carbon here. We could have this here as a sugar. This is the simplest sugar. This is known as glyceraldehyde. Even simpler than this one. The reason why most people don't consider this one though is it's not really natural. It's usually only found in the cosmos, so found in the stars. Right, it's usually where you find these guys. Right, so out in space is where you find glyceraldehyde. So as a very technical, choice as the simplest sugar, that's the one we would go with. If you want to be, if you want to be that kid in class that pushes up their classes, like, oh, I've been reading, and actually, there we go. Well, actually, there is a much more simpler sugar than this one. If you think about it, I mean, carbohydrates, if you just took a carbon, one single carbon and hydrated OHH, and you just satisfied octet, I mean, that's formaldehyde. Technically, formaldehyde is the simplest carbohydrate. So if you wanted to be, well, actually, you could say that. Now, how viable is this outside of just being technical definition? Not very, right? Anyone's familiar with formaldehyde hopefully knows that this thing is toxic. This thing is pungent. It smells terrible. It smells like death. It's associated with death too. It's used in morgues for preservation, I believe. So very technical, but if you want to just be cool, you can say formaldehyde is a carbohydrate, but it's really not. Usually when we think carbohydrate, we think of like pleasant, sweet things, right? Not like deathly pungent odors, right? Cool. So yeah, so those are just some fun little facts. I'll try to keep this to a minimum just to make this video as short as possible. But glyceraldehyde, I mean, that's the simplest sugar, but sugars get complex, right? We can keep adding these carbons here. I mean, glyceraldehyde has a single stereocenter, so it's not too bad to keep track of. Like technically there's two of them. There's this one. I know you guys haven't really thought about stereo quite a bit, but we will have to think about it for sugars, unfortunately. But with this guy here, I mean, there's so many stereocenters, right? Like wedges and dashes, like whether something's a wedge or dash will completely change whether it's a certain sugar or not. And how I can draw this can vary, right? Like what if I chose to draw the mirror, like the mirror of this, or like, the opposite side of this, where 1, 2, 3, 4, 5, 6, right? Like now suddenly everything's going to be switched, right? This is going to be dash, this is going to be wedge, right? This is dash, this is wedge. This is representing the same molecule, right? But think about how much of a headache this is to have to keep track of, right? The fact that you have to keep track of what everything is. So your chemical ancestors kind of came up with an easier way to think of sugars, like kind of a one and all, like way that if you draw sugar this way, you kind of always know what it is. And that's the fissure projection. But to kind of understand what the fissure projection is, right? Essentially what it is, you're taking your sugar, whatever it is, and you're kind of like grabbing the ends of it and you're pulling them down. Okay, so you're kind of bending the spine such that, your aldehyde or your carbonyl or whatever your thing is in your alcohol are here. And then all these alcohols that were kind of in the middle of the molecule, these secondary alcohols, kind of all rotate up just like that. Okay, just like that. And so the visual aspect, what is you're looking at? You're looking at from the top here. What is that we see? Well, what you're going to see is sort of like these arms that have alcohols and hydrogens on them. So like this, right? It doesn't matter exactly where they are. I'm just kind of randomly drawing them in. And then you'll see like the aldehyde or the ketone or whatever at the top. And then the CH2OH at the bottom. Just like that. And so that's what the fissure projection is. It's sort of this bent sugar where you're pulling it down and you're viewing the backbone of the molecule. Now, what do these lines represent in terms of stereochemistry, right? Because we still need to know what is dash and wedge or what is R and S. And so if you think about it, these OHs that are facing your eye, those are going to be kind of like wedges, right? Because they're facing towards you. So every vertical bond you see, I won't draw, actually I just can draw all of them, but these are basically wedges. Okay, so we get perfect stereochemical information here. Right, those are wedges there, and then we have CH2OH, and then we have the aldehyde, right? So because they're pointing towards your eye, that's why they're wedges. The backbone, though, it's being pulled away from you. So this vertical is actually going to be dashes. It's all dashes there. Okay, so vertical bonds are dashes in the fissure, and wedge bonds are going to be, horizontal bonds are going to be wedges. And that's where our stereochemical information comes from in these fissure projections. Okay. Now, this still doesn't really answer the question of how do I know something's RS? Like if I had to, switch between the linear and the fissure form, right? If that was a question I had to do, how could I do that, without having to think about all these like mind-breaking gymnastics? Very simple. If an OH is facing to the right, that signifies to you that center, that wedge center is going to be an R. And if it's pointing to the left, that signifies to you that is going to be an S center. There you go. That's it. So all you have to do is look at the fissure and think, okay, if it's on the right, it's R, if on the left, it's S, and then just convey that information onto the actual molecule. So this first OH here is R. So maybe I make this a wedge and I think, okay, OH is 1, carbonyl is 2, and this is 3. So when I do my line there, is that an R line? Yeah, it is. So I'm going to keep that a wedge. Let's say that this was actually on the left and you wanted to make it S, you would just switch this. So switching dash and wedge on the OH will switch whether it is RS. So I always recommend do wedge first, what I meant to say. Do the wedge first, and once you figure that out, move on to the next one. Or if it's not right, then just switch it. There you go. Cool. So now you guys are all experts on figuring out how to switch between linear and fissure in case that's something you have to do. Okay. But this is usually the form we'll see sugars drawn in, and it's the form that you want to be very, very comfortable with understanding, because you're going to see this for basically the rest of sugars, which is, Wednesday's quiz. Cool. Right. So sugars. So with that, there are some nomenclature things we need to know about sugars. I always hate this part, so I'll try to get through this a little quickly. do my best. Okay, because I just want to get, we just want to get into the reactions, right? That's the most important part. So we'll try to get through this a little quickly, and then I'll leave the rest to Dr. Levens to kind of, explain the rest of the nomenclature. Hopefully, rely on that. Okay. There's also the other video. I'm pretty sure I talked a little bit of nomenclature in there too. Okay. But cool. So we have sugars, and we have different ways of naming sugars, right? The obvious way to name a sugar is just to say its actual name. So actually, let me actually make this a specific sugar, because I know some of these sugars. And at the end of this, you guys will know some sugars by heart too. For example, this here is a glucose. It is a type of glucose, and we'll get to what type it is. But for now, it's just important that we recognize this as glucose. Okay. But this is a glucose molecule, and there's a couple things that we can say about it generically. Okay. One thing we can say about it generically is that, for one, it has an aldehyde top. So we can call this an aldose. Okay. Ose is the suffix for a sugar. So anytime you see ose, you want to think sugar. Do not confuse it for ace, which is for enzymes. Okay, that's something we'll see later. So whether something is sucrose or sucrase will tell you if it's the sugar ose or if it's the enzyme ace. Okay, so cool thing there. But we can call this an aldose because it's an aldehyde sugar. But maybe I want to get a little more specific. Maybe I want to convey how many carbons are in there. We can do that. I can count this 1, 2, 3, 4, 5, 6. All I'd have to do is insert in between the ose and the ald the suffix for 6. The suffix for 6 is going to be hexose. Okay, so this is an aldohexose. Okay, so sugars that are 6 carbons long and have an aldehyde we call aldohexose. Okay, we have other number names too. The ones that are usually the most not confusing, but maybe you didn't know this. CHO is that's another thing for aldehyde, by the way. So if you see both, don't be afraid. It's the same thing. But the 4 carbons, also a weird one. We call this a tetrose. Okay, so we call this a tetrose. So this would be an aldotetrose. Okay, that glyceraldehyde we talked about earlier, right? That'd be a triose. So this here would be a triose. Okay, so an aldotriose is what we would call that. Okay. There really isn't a monos unless you consider formaldehyde a carbohydrate, so that doesn't really exist. And then glycoaldehyde, again, no one really considers this a natural sugar unless you're being snarky. So there isn't like a diose. But triose, that's the quote unquote simplest sugar. We can call that. We have trioses, tetroses, then we have pentoses, that's just 5, and then hexoses. I don't think we're ever going to go past hex, but I believe the next would be heptose, and then octose, and then nonos, whatever. Probably that's what the rest of those are. Just know up to 6, and you'll probably be fine for the class. That's all you really need to know. Okay, so just count the carbons. I'll tell you whether it is, tri, tech, pent, ald, hex, and then look if there is an aldehyde. If there is a ketone, right, ketosis also exists. That's when we see these CH2OHs at the top of the molecule, and we see, a ketone embedded inside. This is the simplest ketone. This is known as dihydroxyacetone. For these, we just call these ketoses. So if any of these had ketones, so let's say this one here had a ketone instead, we would just call this a ketotriose. Now this is just a ketotriose. Okay, so we can build some very generic names to just identify a class of sugars, right, up to the point of how many carbons there are and whether it has a ketone or an aldehyde. But that's not going to cut it for talking about sugar specifically, right? Because I could have glucose that looks like this, right? So I'll go on the next page here. So I can have glucose that looks like this. Sometimes I'll get lazy and forget to write in H's. So if I do that, I apologize. It's just because I'm trying to get through things at a good pace and not spend too much time on this. But I can have glucose that looks like this, right? And I can have another aldohexose that looks almost exactly the same. it looks almost exactly the same. In fact, like the last three secondary alcohols are exactly the same. But this secondary alcohol on the second carbon is not the same. So they are both aldoses. They both have this, 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 and this, but they differ on this one carbon here. They differ on that one carbon there. When we have a difference on one carbon, we call these epimers. So this here is mannose, okay? And we call these epimers, right? To be more specific, we label the carbon that they are epimers at. So this would be carbon 1, 2, 3, 4, 5, 6, and carbon 2 is where they differ. So we call these C2 epimers. That's where they differ. So we can get even more specific. If I know what a sugar is, like if I know if I know a similar sugar and it only differs at one center, I just say, hey, that C2 epimer of glucose, that's what I'm talking about. And hopefully, if the person doesn't know it's mannose, that's fine, but they should know what a C2 epimer is and hopefully know what glucose is, right? So it's another way to communicate information that these guys are C2, or sorry, how these guys are related. So it's C2 epimers. Now, how is it that I know these names and how is it I'm having such an easy time with them? It turns out that there's a cool little trick you can do. So everyone take their right hand and make a middle finger. Yeah, totally. So it's like you're flicking me off. You're like, man, you got this video out so late. We don't care that you were having fun in Oregon. You should have made the video years ago. I apologize. I should have. Just got busy. But you can make a middle finger. And if you think about it, on your middle finger, on your right hand, your thumb is going to be the aldehyde. And your fingertips are the OHs. Wow. So glucose is just a big, big middle finger to the man. That's all that is. So everyone knows what glucose is. It's on your right hand. So none of you should have a hard time remembering that. Dr. Levin is probably really confused while you guys are flicking off, the nothingness during the quiz. So it's a good little mnemonic. Mannose is a finger gun. That's how I remember that one. It's a finger gun. Okay. So 2 sugars you just know for free. It's usually the ones you need to know. The third one you need to know as well usually is fructose, which fructose is very, very similar to glucose and mannose. They have, glucose, mannose, and fructose all have the same, bottom build, right? All this is the same here. But it's the top 2 carbons that would differ for all 3 of them, right? These 2 differ in that they are C2 epimers, right? Fructose differs in that it is a ketose. So it is a ketohexose. This is fructose. Okay. So if you can remember glucose, right, and you remember mannose, or as long as you remember glucose, just remember that the top 2 carbons are what differ across these 3. Usually the 3 that you need to know. I think you need to know probably, there's some that are in your notes probably, and I'll check them at the end. There was someone, shout out to Leslie Wasi. They sent me their notes in the chat, so I can reference that afterwards to make sure. Any sugars that you need to know, I'll just tell you to know. Cool. All right. But this is fructose. And again, this is a ketohexose. Okay. And so again, as you know, fructose, and I said, hey, what is the C3 epimer of ketohexose? That shouldn't be too big of a deal because you just look 1, 2, 3. Oh, the C3 epimer is just going to be flipped like that. Just like that. Not too bad at all. Okay, cool. All right. So that's for the most part, the nomenclature, the basic stuff. The more complicated stuff, or the stuff that's usually the most difficult initially, is the last bit of information. And that is, indicating, I mentioned that there is actually, this is a type of glucose. This is what we call D-glucose. There's also an L variant. So where does that stuff come from? So if we go back to that simplest sugar, right? We go back to glyceraldehyde, right? Technically, there's 2 configurations of glyceraldehyde. Right, so there's glyceraldehyde that looks like this and glyceraldehyde that looks like this, right? These are both the same. They're both aldotrioses. Okay, both look like this, like in a linear form. The difference is whether we have a wedge center here or if we have a dash center. So the difference is whether this is RS, right? So this here is R and this here is S, okay? So that's the differing point between these 2 glyceraldehydes. Well, it turns out if you put these in a polarimeter, which is like a cylinder, and you shoot light through it, and you have your sample here, you shoot light through it, and it diffracts a certain way, and there's a readout, a machine reads out what that diffraction is. Turns out that the R variant spins light a certain degree dextrorotary. So we call it this plus sign here. So this would be plus glyceraldehyde. And this here, since it's the enantiomer, it's going to be equal magnitude, but just opposite spin. So this is a levadirotary glyceraldehyde. Okay. So the simplest sugars and simplest natural sugars, right? The right-facing OH, right, gives us a plus spin, and the left-facing OH gives us a minus spin. To kind of summarize this, what we say is that this is a D-glyceraldehyde. So we say plus D-glyceraldehyde. And then here we say a minus L-glyceraldehyde. Okay. Now in nature, right, sugars don't just spawn out of nowhere. They're built on top of each other. Particularly, we take like a glyceraldehyde, for example, and you build it up linearly. So you build it up this way. So if I wanted to make the next level sugar, this sugar here, which, oh, I know the name of the sugar. I forgot what it is though. It's a symmetric sugar. But this sugar here is built from D-glyceraldehyde. Okay. You could also build with the L-glyceraldehyde, right? You could just do the L way, right? You could build a sugar from that, right? In nature, it would just build on top of it, right? So maybe I do this. So we can build this sugar here. Well, actually, the last reaction we'll learn will actually show us how we can do, make both of these. We can actually do that too. So nature does it, the lab does it too. Okay. Now, because we are building, in nature, sugars are built from the simplest sugar, D-glyceraldehyde. The D in D-glyceraldehyde or the L in L-glyceraldehyde tends, is going to float into the names of those sugars built from them. Okay, so to kind of help make this make more sense, actually, why did I erase that? Right, because let's say this sugar here is built from, let's actually not look at this one. So because this sugar here was built from the D variant, right, the D-glyceraldehyde, this is known as a D sugar because it retains that D-glyceraldehyde component at the bottom. So this here is D-glyceraldehyde, right? That component is retained. So we call this a D sugar. If I used L-glyceraldehyde and I built some sugar from this, and maybe I do a couple different transformations. So maybe I add a couple different OHs here, right? Doesn't matter how many I add, but because I still have this component here, right? The L component or the L-glycerol component, I call this an L sugar. So that's where the D and L naming system comes from. It comes from the fact that sugars are built from the simplest glyceraldehyde. And so what that configuration is of that simplest sugar will determine whether it is D or L, right? So if it's right, if that highest stereocenter is right facing versus left facing, it's a D or L sugar. Now, one thing that students get confused a little bit about, because it's not always explained well, and I bet I didn't do a good job explaining this either, is the idea that if something is D or L, it also tells you about its plus or minus. Here's the news on that. Whether this center is right facing or left facing, so whether this is right facing or left facing, tells you if something is RS. So if it's right facing, it's definitely R. That will also tell you if a sugar is D or L, right? So if it's right facing, it's D. If it's left facing, it's L. The one thing you will never know, though, in this class, unless you're told, is whether something is plus or minus. So D does not mean something is plus, and L does not mean something is minus. There's no bearing on that at all. That requires a polarimeter, right? Again, we just found out that the right-facing OH on glyceraldehyde is positive, it's dextrorotary, and that's why we called those sugars based on a D-glyceraldehyde, or sorry, a D sugars, right? Same thing with the L, right? It just turns out that the left-facing OH is levadirotary in polarizing light. And so that's why sugars built from that are called L sugars, but it has no bearing as to what those sugars will be at the end. Absolutely no idea. We don't know. So very good question you could be asked is you're given some sugar and you're asked, is this sugar D or L? Right. And so again, doesn't matter whether it's keto or aldose. All you have to look at is the final stereocenter, the center that would have been derived from D-glyceraldehyde, because again, we build our sugars linearly. So this would be the part from glyceraldehyde. If it's right facing, it's going to be an R center, which does mean that it's D. But if you're asked whether it's dextrorotary or levadirotary, you do not know. You don't know which one it is. Okay. You can have levadirotary D sugars. That is totally fine. You can have dextrorotary L sugars. That's totally fine. And you can have the opposite as well. but you just don't have that information. You don't know unless you're told beforehand. Unless in lecture she told you these sugars have these, you don't need to know any of them. Okay. The one that you should know though is glyceraldehyde and in its D and L form, because that's where everything was built from, right? One little anecdote I like to tell people that kind of helps them sometimes is this little story that when when your chemical ancestors were coming up with this, they, when they figured out that the right facing OH is dextrorotary and left facing OH is levatorotary, they naively thought that every sugar with that component also had that feature. And so they erroneously, called all those sugars D and L because of that, but later on found out that it was wrong. If that story helps you remember it, you can use it. I just like telling it. Also just kind of a way to remind you guys that, hey, everyone makes mistakes, right? Even your chemical ancestors that, even they had a dull moment. So if that helps, you can use that. If it doesn't, it's okay. Again, point being is that you have complete conveyance of information on whether something is S, R, or D and L. You have absolutely no way of figuring out if something is plus or minus without having been told beforehand. Okay, so who knows? Who knows if something is actually plus or minus? But we do know something is a D sugar or an L sugar, and we do know something has an R center or an S center. That's totally possible. Okay, cool. So I can have, again, if I go back to that glucose molecule, right, and I look at this, right, again, if I look at that highest stereocenter, right, that's right facing, right, that center that is from the glyceraldehyde, that's going to be a D sugar, right? It's going to be an R center, right? So it's a D sugar, right? I could also even take glucose and then switch it on that C5, right? So 1, 2, 3, 4, 5, that 1, 2, 3, 4, 5, that highest stereocenter, I can switch it on there, right? And now it's going to be, right, this here that's derived from the glyceraldehyde. Now that's going to be S, which is going to be an L sugar. But do I know if it's dextrorotary or levatorotary? I actually don't. I don't know at all. I have no idea. But I do know whether it's D or L. But I don't know if it's plus or minus. No idea. Okay. So plus or minus, I don't know. Now, one last thing on nomenclature before we move on to reactions finally, is when we look at D-glucose here. So this here is D-glucose. Okay. And I switch on that C5. So I make the C5 epimer. So this is a C5 epimer of D-glucose. Okay. Does switching on that C5, you think, turn this into L-glucose? So what I call this L-glucose, is this sugar L-glucose? It's definitely an L sugar, but is it L-glucose? Right, think about that for a second. So this is always usually a confusing question, and I think that most people can usually guess the answer, although they may not be confident. But there's a really easy way to prove this to yourself, right? Let's take this sugar, or sorry, let's take actually, a second of that useful. Actually, yeah. I guess I'll just tell you. I had an example in my mind, but now I think I might confuse you guys more because it's confusing me in my head. So it might confuse you guys if I say it out loud. The answer is very, very succinctly that this, in fact, is not L-glucose. Right. This is the C5 epimer of D-glucose, but it's not L-glucose. So it is a L sugar. It's just not L-glucose. When we say D or L of a particular sugar, we're talking about enantiomers. Okay, so we're talking about enantiomers. Right, so in this case, the mirror image, just like that. This here would be D-glucose, which I'll say D-glu, and this here would be L-glucose, which is L-glu. Okay, enantiomers or D and L sugars of the same name are always enantiomers of each other. Okay, which should make sense, right? Because if you think about it from the L-glucose standpoint, if I just switched on C5, right, this wouldn't make D-glucose, would it? Oops, sorry. Wait. Oh, I'm drawing the wrong one. Okay, sorry. So if I just switched on C5 like this, this, it probably makes more sense now, right? If I just switch C5, then I made the C5 epimer of L-glucose. This is not D-glucose, right? This is D-glucose. We know this to be D-glucose. So the C5 epimer here, and clearly of L-glucose, is clearly not D-glucose. It's D something else. I think it's idose. That's the epimer. I can't remember off the top of my head though. Okay, so D and L sugars or D and L variants of the same sugar are always enantiomers. They're always mirror images. Everything is flipped. But if you just do like a C5 epimer or just an epimer of that highest stereocenter, that is just going to be the D or L sugar of some other sugar, not the same one. Okay, cool. All right, so that's nomenclature. Again, I'll hope Liebens covers that better than I do. That's just meant to be very brief. But yeah, so we can move on to, I guess actually, for those of you that are watching this probably really early in the morning, right before the quiz, I'll very briefly cover cyclization in case you need it. Like if you don't have the 20 minutes to watch the other one. But if you do, then you can skip through this part. Just watch that other video. But, sugars, for the most part, spend a lot of their time cyclic. They spend 99% of their time cyclic. So it's really important we know how to cyclize these. I'll use D-glucose as the standard here. But there's two cyclizations you can do. You can do a pyranose cyclization, which is going to be a 6-membered cyclization. And you can do a furanose cyclization, okay, which is a 5-membered cyclization. Okay, very easy to remember. The F in furanose can stand for the F and 5, and then the P in pyranose can stand for the P in pix or 6, whatever you want to, whatever you need. Maybe P, this upside down is a 6. I don't know, whatever you got to use to remember. I think if you just remember this one, you remember this one. Okay, cool. And so we'll work on one of these at a time. Fun little fact, you don't actually know what a sugar prefers, whether it prefers pyranose or furanose, unless you're told beforehand. So if you're given no information, you just kind of have to assume, or you're told, right? You don't know. So you'll probably be told if you need to draw a pyranose or a furanose, or there'll just be those available, I suppose, and you just choose the one that matches your molecule. Just in case. Okay, cool. So let's just make the pyranose. Again, pyranose is a 6-membered ring where we have an oxygen in the, inside that ring. So one of these OHs here is what's going to cyclize to give us that oxygen here. Even this one could do it too. The way that I figure out which one it is anytime you do a cyclization, let's say from this OH here, you attack on this carbon here, right? On the aldehyde carbon. So let me actually draw this out. You attack on this aldehyde carbon here. So if the oxygen of one of these alcohols, right, any of these alcohols here, is just attacking on this carbonyl here, the oxygen you can count as 1, and that carbon you attack you count as 2. Or in other words, the carbonyl carbon is carbon 2. So what I do is I just start counting from 2 on the carbonyl carbon, and I just work my way down to the number that I want. So to put that into perspective, or to put that into play here, that'd be like 2, 3, 4, 5, and then 6. I wanted a 6-membered ring, so I just stop at 6. That means that this OH here is the one that cyclizes. That's oxygen 1. Okay, so that's how I get that. So 6, so 1 here attacks 2, and 2 is a carbonyl. So when you attack on the carbonyl, remember, alcohol and carbonyl, that together makes a cyclic hemiacetal. That's why these are so favorable, right? We have a cyclic hemiacetal here. Okay, that's why sugars, again, cyclize. Why we expect them 99% of the time to be as a ring. Okay, a hemiacetal, just very generically, is an OH, right? It is a carbon with an ether or an OR and an OH. Now, to put this into perspective with sugars, right, all that really means is the OR group is just, connected to the rest of the molecule. So it's just a ring like that. Okay, so that carbon here, this carbon 2 over here, is going to be hemiacetal in nature because this 1 attacks the carbonyl 2. So we'll have here an OH and an H. Okay. Now, is there anything on the aldehyde that indicates whether that OH is going to be facing up or down? Absolutely not. Although we do have names for it. So when it's facing up like this, we call it beta. When it's facing down here, we call it alpha. So if there was an OH here, we would call that alpha. Okay. Whether something is alpha or beta, you have absolutely no idea. That's just going to come with, either you're told or you're given information beforehand that a sugar prefers alpha or beta. Okay. But I will choose to just put it beta for now. just because I have the knowledge that beta pyranose for glucose is preferred, and now you do too. But carbon 2, you don't know, usually given for free. So again, the beta state, alpha beta state, and the pyranose furanose state, is this going to be information that's given to you for free, or it's just going to be there and you have to figure out, from that which sugar is yours, right? Cool. So carbon 2, that's going to be, we have a name for this actually. We call this an anomeric carbon, then a different color. And we'll come back to this term a lot. Okay, so just know it, anomeric carbon. Okay. Again, we'll just make it beta for the time being. But every secondary alcohol after this, we actually have explicit information as to whether or not it is up or down in this system. It's very simple. If it's on the right, it's up. If it's on the left, it's down. Oh, sorry, other way around. If it's on the right, it's down. If it's on the left, it's up. Okay, so that's how it works for these D sugars. Okay, so carbon 3, we have bonds that look like this and this, and we have a right-facing OH, so that OH is going to be down. Right. Carbon 4, we have up and down, right? We have a left-facing OH, so it's going to be up, so it's going to be over here. Right. Carbon 5, we have bonds that look like that. We have a right-facing OH, so it is going to be down. So that's going to be this bond here. And then in carbon 6, we have an OH that is facing down because it's on the right. But hey, hold your horses, right? That OH is O1. That is the cyclizing O. So don't just accidentally put on here a down OH. That's not what we want to do. Keep in mind that that oxygen is in the ring. So what's going to come off of 6, that's just going to be whatever is below 6, right? Below that whatever is below that carbon 6 is what's going to show up on that carbon there. So all of this here is what's going to show up. Okay, so all this here is what's going to show up on carbon 6, CH2OH. And so where's it going to go in space? Does it go up or down? Well, it's very simple. If the cyclizing O is supposed to go down, then everything that's going to come off of 6 is going to go in the opposite direction. This is going to go up. Okay, so CH2OH is going to go up like that. Okay, so here comes our first little trick for the evening. Where in the world, or how do we tell DNL from a cyclic sugar? If you have a CH2OH on this carbon on the clockwise to the O, right? Or if you have this like CH2OH, I mean it can even be here too, right? As long as on the counterclock side of that cyclic O, you have a CH2OH, whether it is up or down, completely choreographs to you if it's a D or L. If it is up, this is a D sugar. If it is down, it is an L sugar. Okay, so if you have a CH2OH coming off of that, last carbon on the ring, right? That is going to tell you immediately whether it's up or down if it's D or L. Okay, so that's the first trick of the night, how you can tell those very quickly. Cool. And with that, that is our beta glucopyranose. Okay, glucose in its 6-membered form. A very quick and easy way to do that. Okay, cool. All right. So I'll go ahead and draw another one of these glucoses so that we can do the 6-membered. Again, I'm going to go through this a little quick just because I spent 20 minutes in that other one kind of going through this a little more like slowly and in depth. I just want to get this out of the way. Just in case you have to, you only have this one resource to do this. But now if I want to do 5, again, I'm going to do the same counting, right? 2, 3, 4, 5. 5 is where I want to be. So I'm going to cyclize on that OH there. So if I kind of do the same numbering in here, that would be 1, 2, 3, 4, and 5. Right? Remember that anomeric carbon 2, the one where we attack the aldehyde, that is going to give us an OH and an H, but we don't really know where it's going to be because that's depending on if it's alpha or beta. I will just go ahead and do alpha this time. Sorry, I'll go ahead and do alpha this time just because I did beta last time. So let's go ahead and do that. But everything after that, it's kind of choreographed, right? If it's on the right, it's down. If it's on the left, it's up. So we can go ahead and mark these in. So 3 looks like it's down, 4 looks like it is up, and then 5 looks like it's down. But again, hold your horses. That OH is a cyclizing OH. That's OH1, right? So everything below that is what we care about. So all this down here is what we care about coming off that carbon 5. So it looks like we're going to have a CHOH coming off of that, and then a CH2OH coming off of that. Okay. Now, this is a stereocenter, so we do have to define it, R and S, and that's pretty easily simple. Remember this H here, OH here is facing right. So if it's on the right, it's going to be an R center. So what I like to do is I make this a wedge, and then I say, okay, OH is 1, ring is 2, this is 3. This is always going to be the case, by the way. OH is always 1, ring is 2, and this is 3. And this gives me, looks like a clockwise spin, which is indicative of R. Okay, so that's what I want. Now let's say this OH were on the other side. How would I get that to match? Very simple. Just switch it to dash, and it would match. Okay, cool. So that is going to be my completed pure nose with my extra stereocenter, which brings our next trick of the evening. Let's say that I have this sort of chain coming out of that final carbon on the ring, or that clockwise carbon of the counterclockwise carbon of the ring, right? The final stereocenter that determines DNL is going to be this one here, right? The one that's outside the ring. And again, whether it's R or S is going to tell us if it's right or left, or tell if it's D or L. If it's an R center, it's going to tell us that it's a D center or a D sugar. An S center is going to tell us that's L. Okay, so look at that. All that information that we get just from that. Pretty nice if you ask me. This is definitely the hardest one, so don't be too afraid about this one. I'm not sure if this will even show up. I'm not even sure if you even got any practice on that, but that's something that could show up. Okay, cool. So that's how you cyclize sugars. Again, kind of going through this a little fast. So use that other video if you need a more slow and in-depth process. The only one that we haven't covered is if I ever cyclize and this carbon here is a CH2. So let's say that I get, this, and then something here, doesn't matter. If this carbon here is a CH2, so that final carbon in the ring is a CH2, then the final stereocenter, the DL stereocenter is actually going to be this one here. And whether it is up or down will tell you immediately whether or not it is D or L. If this is up, it's going to be L. And if this is down, it's going to be D. Okay. So down would look like if it were here. If it were down, it would look like that. Okay. So these are the three cases in which, you would have to determine D or L just from the ring shape. And again, you can look at the final carbon. There's a CH2OH, whether it's 5 or 6 membered ring, right? If you see that CH2OH being up or down, will tell you if it's D or L, right? If it's a stereocenter outside of the ring, right? If it's RS, will tell you D or L. And then if it's a CH2 on that last carbon, you look at the carbon before that, and whether it's up or down will again choreograph if it's D or L. Okay, cool. All right. Now, one last thing for these that, can be a little difficult is, let's say that you're given a sugar. So I will just very quickly do this. Oh, actually, before we do that, one thing we'll do on here. So one other question you could possibly ask is, whether sugar is aldose or ketos from the ring form. It's pretty simple how to figure that out. Aldoses on the anomeric, right, on that C2 will give you an HOH, right? Let's say I turn this into a ketos just for the sake of, seeing this. Right, a ketos just turns the aldose H into a CH2OH. So that just means that here, there would just also be, let's say I look at this one here, there will just also be a CH2OH here on the anomeric carbon. Okay, so ketos, aldose, very, very choreographed, right? Right, whether it is, right, this or this, right? That's very, very obvious to us what it's going to be. Okay, so you can use that to figure that out. Cool. So one last thing, sort of another hard problem, variant of the problem. Let's say that you have some random sugar, which I'll just quickly draw in a pure nose form. So that would just mean cyclizing like that. So if you want to, you can pause and try this, but I'll just write some stuff in. Oh, I meant to make this random. So I will make it random. I'll change it because it's glucose again, and I want it to be different. There we go. Okay, cool. So I just drew those in. I'll just put this here. It doesn't really matter. Again, C2 doesn't matter, but C3 is going to be down. C4 is going to be up. This is also going to be up. And then since this cyclizing is going to be down, but this should then be up. Okay. So this is your cycle. Let's say that you're told or you're asked to give you're only given this. Let's say that you're only given this and you're asked to reproduce like the C4 epimer, right? Or you're asked to reproduce, just some epimer on any carbon. It's very, very simple. Okay. The counting, right? I know I count here too. That's just for the purpose of cyclizing. The counting is always that anomeric is 1. So 1, 2, 3, 4, and then 5 and 6, right? If you're asked for the epimer of any of these carbons, just flip them. So let's say C4 epimer, right? Everything should stay the same. right? Anomeric, it doesn't matter. Again, anomeric doesn't matter. So you can kind of, essentially you can ignore C1. That one you can always ignore. Like, who cares? Right? It could be anything. It's anomeric, right? Unless you're told otherwise, you don't know what that is. But C4, right, is this guy here. That's the epimer. So just flip it. So it should be now down. Now it should just be down. Okay. So I just drew the C4 epimer of glucose. So let's say you're giving glucose and you're asked for the C4 epimer, right? That would be this guy. Let's say you're asked for the C3 epimer of glucose, right? Same thing, right? Who cares about anomeric? That would be carbon 1. This is carbon 2. C3 is this guy. So now it's going to be here. That's a C3 epimer of glucose. Okay. So if you're ever asked for epimers of ring forms, just flip the carbon, or flip the OH, whether it's up or down. Don't stress over it too much. Just keep in mind for ring form, I know that I do the counting where this is 2, but that's just for cyclizing purposes. Really, when we do counting, this is 1, 2, 3, 4, 5, 6. So for epimer numbering, right, carbonyl is 1, or C1 is the anomeric. Okay, just keep that in mind. Cool. But with that, again, I'm going to call it there on nomenclature and cyclizing. Again, watch the video if you need more, slow, in-depth going through. It's 20 minutes, not too bad, I don't think. So yeah, let's go through that. Cool. All right. So that being said, we can finally get into reactions of carbohydrates. And kind of like I mentioned, but I didn't really draw out, right? Carbohydrates, despite the fact that we draw them in linear form, in fissure form, majority of their time spent actually is in their cyclic forms, in their ring forms. Because again, cyclic hemiacetals, very, very favorable. I forgot this here. I have like glucose imprinted in my mind from drawing it so much. So it's like usually the go-to for these. It's like usually what I do. Okay. So it spends 99% of its time as a cycle, 1% of the time as linear. Now, this is kind of an interesting question to think about, right? How, if this is so stable, right? If cyclic hemiacetals are so stable, right? Why isn't it that it just stays as the hemiacetal? Why is it that they're like? How do we know that there's equilibration? That it even opens up, right? Like what gives off this idea that this would even open up in the first place? This is a really good thought experiment. I would, if you don't want to think about this, just want to get to the things, I would skip through this part. But this is, more of a, conceptual idea. But how is it that we know that sugars are equilibrating, right? That they're opening and closing despite it being 99.1? Why isn't this just 100%? Well, glucose actually has two forms, right? It has the alpha and the beta form. So technically there are two forms here. Right. So again, where the OH is down, this is alpha. When it's up, it's beta. This would be the beta form over here. But these are the two forms of glucose. And so technically one is more favorable than the other. Right, you can imagine. I don't know if she told you this, but the beta form in class, or she told that in class, but beta form is the most favorable form, or the more favorable form of glucose usually. Although that is subject to change, but generally speaking, beta is better. And if I were to expose the beta form to plane polarized light, it would turn the thing. It would turn the light to a certain angle. Let's just say plus 10. It's a random number. If I do the same thing with the alpha form, let's say it does like plus 70, just again, some random number. If it were true that a sugar just clammed up once into a ring and always stayed 100% in that ring, right? You can imagine then if I put it in a polarimeter and I read the reading, right, and I watched it, bounce, bounce and refract the light, you can imagine that the reading would either give one of these two numbers, right? Like let's say, again, I mentioned that the beta was the more stable form. If it is true that the sugar only turns into a ring once, right, just clamped into a ring and stays in it forever, right, it's not equilibrating at all, right, it should always give me a reading of plus 10 here, right, because it's always going to be in the beta form that's more stable, right? If it didn't, right, if there was some equilibration, then the number should be different, right? It should be, it should be between 10 and 70, right? Depending on, which one's more stable, will be closer to the stable number. Okay. So it turns out when we do this experiment, the value ends up being something like, could be something like plus 20, a value that's close enough to 10, even we can even do 30, right? Close enough to 10, but it's definitely not error. And that suggests to us that, although beta is the most stable and, these guys like to be rings, it is still opening and closing. So these sugars, in a sense, are breathing, right? It's becoming beta and then opening up to linear and then maybe going to alpha or maybe going back to beta, right? These sugars are opening and closing. It's like lungs, kind of. So cool little thought experiment, right? How do we know that it's 99 to 1 and not just 0 to 100, right? Well, one way is to just, throw it into a polarimeter, look at the plane polarized light rotation. If it were not one of these absolute values, right, then there has to be some kind of equilibration, right? And that's the case that we see. Okay, cool. But anyways, all that is just some, theoretical, or all that is just fun thought food. But although we consider the ring form to be the most dominant form, actually a lot of reactions that we do on sugars concern the linear form. So it's that 1% of the time that we're trying to capture that open linear chain that does the reaction that tells us, oh, okay, there's a sugar there because it's reacting with the material. So the first couple of reactions, the redox reactions, we'll talk about, and then the elongation reactions actually depend on the linear ability. But all this equilibration stuff wasn't just for nothing. What's really important is that if we're going to do a reaction with a linear form, that this equilibrium exists in the first place. So we'll come back to this and we'll talk about an example where maybe that equilibration doesn't actually exist. Maybe something prevents it, and so those reactions are lost to us. Okay. So again, that equilibration to 1% is going to be important for these upcoming reactions. So we'll talk about redox first. Now, to kind of give you guys a little bit of context to help make these reactions make more sense, why we talk about them, is that we're kind of walking in our chemical ancestors' shoes and seeing how they did reactions, how they figured out which sugars were which sugars. Actually, a lot of these reactions we're talking about were done by Fissure himself. So the guy that made the projection, he actually is kind of the pioneer, and he characterized a lot of sugars in a very clever way. In fact, actually, some professors will spend whole lectures talking about how he did it because it's so fascinating. But we don't care about that, right? We just want to know what he did. So if it helps you, think of the context of, if you're trying to find some context as to why these reactions are important, think about, this is how Fissure figured out that this sugar was an aldose or a ketos, or if it was, reducing or non-reducing. That's exactly what he was doing when he was, doing these tests. Okay. So the first redox test we'll talk about concerns the reduction capability, or the oxidizability, I suppose, of sugars. Okay. So generically, I mean, if you think about a sugar, right? Again, there's three reactive areas, right? We have the carbonyl, right, which I try to get in the habit of drawing it out a little more. So we have the carbonyl. We have these secondary alcohols, and then we have these primary alcohols, or the primary alcohol. And if we think about which of these three is the most, accessible, the most reactive, it's definitely going to be the aldehyde. So a lot of redox chemistry deals with the aldehyde, or the carbonyl, and transforming that, especially in the first two tests. So the first two tests, you might have seen the names Tollens and Fellens. Okay. I believe you guys do this in lab, or you do a different one. I don't remember. But Tollens and Fellens, these are basically basic metals. So for example, I believe, I might get this wrong. I probably will. I think Tollens is the Ag2 plus and OH minus, and then Fellens is Cu2 plus or Ag plus. I don't remember the charge state, whatever. But I just remember that you just really know it's a metal, right? It's a metal in base. And so sort of the point of these is that if you look at these metals, they are positive, right? They are looking for electrons, okay? So if they're looking for electrons, they're trying to pull electrons out of this system here, right? What they're trying to do is oxidize the sugar, okay? So these metals are attempting to oxidize this sugar here, right? Again, the most oxidizable position is going to be this aldehyde here. And if you think about aldehyde oxidation, right? Aldehydes can only really oxidize to one other thing, right? They oxidize into carboxylic acids. Okay. So these tests here, you don't need to know how. That's a bit of the complicated stuff, that you don't need to worry about that. But the point is that in these basic metal solutions, aldoses will oxidize into carboxylic acids, or what we call aldonic acids. Okay. Now, again, because they are reducing the metal, right? The metal is oxidizing the system, right? It's turning it into a carboxylic acid. That means the aldehyde is reducing these metals, right? Aldose sugars we call reducing sugars. Okay. So if we have a carbonyl, right? Like an aldehyde, right? We call this a reducing sugar. Now, another really important thing that may not be super obvious now is that that really means that, again, if a sugar is spending 99% of its time in cyclic, right, it's really important that this cyclic sugar stay hemiacetal, because we still do need the equilibration, right? We need the ability to turn into our linear form so that we can capture that 1%, right? Because eventually, once it turns, it will capture this and turn it into the aldonic acid. The aldonic acid doesn't equilibrate, by the way, like that doesn't equilibrate. So once we capture this, it can't form into a cycle. Usually not. Okay, so it's also really important. Again, we'll come back to this, that this is a cyclic hemiacetal. So if you had to figure out from a cycle whether it is reducing or not, just look for the hemiacetal, right? Look for the anomeric carbon. Make sure there is an OH, right? If you have an OH, right, you're good to go. You're good to go there. That's a cyclic hemiacetal. Okay, so again, phenolens and toluenes, the traditional reducing sugar tests, right? Aldoses will respond perfectly to these. And it sort of makes sense, right? We know that aldehydes usually respond to oxidation by turning into carboxylic acids. So when we think of ketosis, then that might be a little tricky, because we think, okay, a ketose, well, that's a ketone. And last I checked, ketoses don't really turn into carboxylic acids. So this might lead to two thoughts, right? It might lead to the thought that, ketoses are not reducing sugars, right? They should not respond to the test, right? I guess that's probably the biggest thought, right? Two thoughts are, I guess the two thoughts I meant is this, is that one is that they shouldn't respond to this test. They shouldn't turn into anything. And then two, that by default then means that they're not reducing sugars. But it turns out they do respond. And the product of that responding, or sort of the product that's, showing a signal, right? Usually when you do this in lab, it's very obvious. I forgot, it precipitates. I forgot what it turns into, what color it is, but it turns into something. But usually what you'll see is it turns into this. It turns into a COH, which that's kind of weird, because how in the world is this position oxidizing? Just a second ago, we said that we needed the aldehyde, right? The aldehyde, that we understand. Aldehyde turning into carboxylic acid, I totally understand that. And I imagine you guys understand that too. So what in the world is going on that is allowing this ketose to respond? Because if it responds, that means that ketoses are also reducing sugars, right? So as long as we have, let's say we have a ketose here, as long as we have that CH2O, I mean, as long as we have an OH on that center, this is going to be reducing, right? So how is it that ketoses are able to respond? Well, it kind of goes back into the fact that this is in a basic solution. So I'll just draw a generic. I'll just draw glyceraldehyde. I'll just draw glyceraldehyde here. Or actually, you know what? This might be long, but I'll still draw. We'll talk about glucose. Yeah, we'll talk about glucose, but I won't draw all of it. Just the part that matters for this reaction. Okay, so I'll draw glucose just to start here. D-glucose. But let's say I have D-glucose and I put it in standing base, okay, or I put it in basic solution. Okay, think back to the last chapter, right? When we think of the a base and the functional groups that I have, right? I have alcohols and I have carbonyls. Remember, base and carbonyls, that makes a particular structure, right? If I have a carbonyl, that hydrogen there is particularly acidic. Bases will like to pull that off, and they'll form enolate structures. So it's no difference here. We have a base and we have a carbonyl that has an alpha proton. Let's go ahead and pull that off. Okay, and so I'll kind of annotate here, but we'll form this enol here, this enolate. Okay, and this enolate will just get protonated in solution by probably water or something. Okay, and what we form is this here. So this looks like an enol. That shouldn't surprise any of you, but it's kind of like a weird enol, right? It looks like a it's a double enol. The name for this is an enediol, and enediols, interesting. They have two sort of fates here. One fate is that we just go right back. That's why I drew in these reversibility arrows. It's because it's totally possible that this enediol just collapses back to the original sugar. So it collapses back to the original glucose. That's totally possible. Deprotonate, and then this goes out and grabs a proton, goes back to the aldose. Totally possible. But again, if the whole point is that we're deprotonating an OH, and there is another one, right? So what happens if I deprotonate this one? Well, deprotonating that one will give me this O- here. And when I go ahead and grab a proton right now to turn this back into a carbonyl, well, wait a minute. That is no longer an aldose. That is a ketos. So it looks like an aldose, when you put it in base, will epimerize into its C2 ketos. Whoa, interesting. And this process is completely reversible as well. So a ketos that is put into base can epimerize into its aldose. Okay. Now, one last thing. This process here, right? We kind of assumed in the backwards that if it were to collapse back to glucose, that the H would add on the same side. But again, we don't actually know that, right? This could grab a proton, and instead we could get addition on the other side. So maybe we make the sugar where the OH is on the other side. So not only do I make an aldose, so I return back to an aldose, but I make the C2 epimer aldose. Okay. This process is what we call base-induced, or I guess we'll just call it base epimerization, just to minimize on words to know. This is base epimerization. And for the purposes of this class, I think the most you'll have to worry about this is with aldoses and C2 ketoses. The idea, essentially, if you think about it, is just that if I have an aldose or a ketos, a C2 ketos, you're essentially sliding the carbonyl across those first two positions, those C1 and C2 positions. Okay. So if I kind of draw this on the other side here, right? So I had glucose, right? I put this in base. Right, I put this in base. What I get is another aldose, again, just a C2 epimer, which, hey, we talked about this. Who's a C2 epimer? Who makes the finger gun? Right, that's mannose. By the way, someone remind me, because I'm going to forget, because I'm going to go to the gym after this. Someone remind me to, I have a nice picture of a mannose reaction that I did. It looks like it belongs with glyceraldehyde in the cosmos. So be a good little treat for you guys. If I don't remember, someone just remind me. But anyways, we can form mannose, right? The C2 epimer, right? But we also form the C2 ketos. So in this case, right, everything below C2 is the same. Just that C1 and C2 are the ketose body, right? So we form fructose as well. Okay, C2 ketos. Okay, so base epimerization. Essentially, the carbonyl is sliding between the C1 and C2 positions, right? And so because of this, I mean, technically you would think that there's only two answers, right? You would think that it's the original aldose and then the C2 ketos that's sliding, right? That carbonyl sliding. Like, remember, in that sliding, we can get an epimerization of that C2 for the aldose to also make the C2 epimer. Okay. So how do I answer this question correctly if I see a sugar that has OH minus? Just make sure you draw, I mean, hopefully it's an aldose, because it can get complicated if the aldose, or sorry, if the ketos is like not C2. So she'll probably keep it to C2 and aldose only. But if you see an aldose in base, just draw the C2 epimer and also get the ketos on there too, the C2 ketos, right? That's the point of the base epimerization. It also then explains to us why it is that we're seeing oxidation or we're seeing a responding test from the ketos, right? The ketos is responding because actually what's happening is it's epimerizing, right? This carbonyl is sliding up to that aldehyde position, that C1 position, and then responding to the test. Okay. Turns out also that you can get oxidation next door too. So we're getting a little bit of both worlds on that. Kind of cool. Okay, cool. So ketoses and aldoses are both going to be reducing sugars. Okay. So both of these will be reducing sugars. Okay. Again, big point here is that you have to have the accessibility of these forms, right? So again, we'll talk about it when we get there, but as long as we have an equilibration, right, between the ketos and the aldose, so you can have a CH2OH or an H here, doesn't matter. As long as we have the hemiacetal center and equilibration, we will have a reducing sugar. That part will respond. Cool. Now, are there any tests? So these tests just tell me if I have a sugar that's reducing or not, right? Are there any tests that tell me if something is a ketose or an aldose? There is. So there is an oxidation that does discriminate between the two. And that is going to be the Br2 or the bromine water oxidation, which I'll just do very quickly here. Bromine water just turns aldoses into aldonic acids. Okay, absolutely no changing of anything. It keeps everything the same. Just changes that OH, sorry, that aldehyde into a carboxylic acid. The mechanism of this, for those of you that like mechanisms, this actually is how the metal one works too. When you make it, like really most all aldehyde oxidations kind of work like this. But the big point here is that when you hydrate an aldehyde, you make the geminal hydrate, right? And then usually one of these alcohols will go ahead and attack an electrophile to sort of activate the structure. So in this case, in the bromine water, the electrophile is bromine. In the metal oxidations, the electrophile is the metal. Okay, so we'll add the electrophile here. In this case, it'll be bromine, right? But what ends up happening is this hydrogen here, the aldehyde hydrogen, right? So this guy over here, I'm just going to pull that off, right? And use bromine as the leaving group or the metal as the leaving group. And so that's what causes the oxidation. Okay, so that's how that works. So in the case of base epimerization, where you can get the aldose regardless of if it's ketose or aldose, you can get this sort of oxidation. But this here is not basic at all, right? There's no OH minus. So a ketose, unfortunately, cannot participate whatsoever, right? This is going to be NR. Br2, H2O is not going to do anything. Okay. So that's a way that you can, if you wanted to, that's a way that you can, or Fissure use to distinguish between a ketose and an aldose, right? A response to this test would have told them that or told you that, as to whether it's ketose and aldose. Cool. All right. You can also do stronger oxidations. If you part of these stronger ones is, Emil Fischer was trying to figure out which sugars were related and, things about their structure. You can do stronger ones. A stronger one that you can do is the HNO3 oxidation, usually aqueous. This one's pretty strong. This will just turn the aldehyde, as always, into a carboxylic acid, but also the primary alcohol. So you see both of these groups getting oxidized in this stronger, much stronger oxidation condition. Second-year alcohols are untouched though, so they'll stay exactly the same. This is an alderic acid. Alderic acid. Okay. And so what Emil Fischer was doing was he was turning sugars into alderic acids to see which ones shared the same middle section, because some sugars. Oh, is it? Wait, was that why he did that? Why did he make alderic acids? Oh, no. Okay, it wasn't those that shared the middle section. It was those, he was trying to figure out which ones were symmetric. Because let's say that I had a sugar that looked like this. Right, this is an aldose, but it's at the moment chiral. But if I do the alderic oxidation where this turns into COOH, hopefully you can see that this is achiral. Right now, this is completely achiral. There's a mirror plane down the middle, right? This one would still be chiral because there's not a mirror plane down the middle. Oh, wait, no, there is. Sorry, there is. There's a mirror plane down the middle. Let me change this, actually. Kind of make my point. There we go. So this is the one. This is part of why he did this one. Is so that, this would still be chiral. So this would still rotate plane polarized light to be polar, but this is achiral. There's a mirror plane down the middle. So that's why he did these tests here. Just a cool little snippet, just to know. But maybe what you guys only care about is maybe all you guys care about is, it turns it into alderic acid. Okay, cool. You can do this test on ketoses as well. So that's why this is not a good test to differentiate aldehydes or aldoses and ketoses. Again, you can oxidize primary alcohols on this. So you would just get this here. Again, the alderic acid. It's just an alpha keto alderic acid. So those are your primary oxidations. Again, main thing to keep in mind here is the fact that the reducing sugar test will turn both ketoses and aldoses into aldonic acids. And again, how do ketoses even respond, right? They respond through the enediol. Really, really important. You might get a question that just asks you what happens to sugar and base, right? Something to keep in mind. And then we have ability to differentiate between aldoses and ketoses. That's the bromine water example. And then just if you want to do a stronger oxidation to tell if, a sugar were optically active or not, or I guess kind of tell what the middle body of the sugar is, you can do the alderic acid oxidations. Okay, it's kind of the point there. But I imagine for most of you guys, you just want to know what things turn into. That's okay too. That's totally fine. Some of you might be wondering, or maybe not be wondering, but I just want to bring it up. One thing that I always wondered is why you don't just Jones these things. And to be very, if you think about it, Jones would be a good contender here. You would only really use Jones in two instances here. One instance is if you wanted to oxidize absolutely everything. Jones would absolutely destroy this. Oh, sorry, I got ahead of myself there. That should be CH2OH. Jones would absolutely eviscerate this molecule. In fact, I'm pretty sure, I don't even know how stable this is. This probably start to, I think Jones could even facilitate bond breaking here. It would absolutely eviscerate the molecule. Something that can do. But that's why we don't do that, right? That's how, if you want to oxidize these secondary alcohols, you'd have to use Jones, but that would oxidize everything in the process. Okay, which this is not a very useful molecule. All sugars will make this molecule, right? All 1, 2, 3, 4, 5, all pentoses will make this. So it's not useful information to us to know that. Okay, cool. So those are the oxidations and all the things that they tell us. We do have reductions. Reductions are fairly simple. You just use something very mild. Okay, for an aldose, right? A reduction would usually use NABH4. You could use something milder. You might also see NABH3CN. I'm not sure, but NABH4 will work here. NABH4 doesn't care about the alcohols in the middle or on the bottom. Just care about the aldehyde. Super, super simple. So let's say that I have it this way. You're just turning it into an alcohol. Okay. So actually, let me just put it this way. So whatever the aldehyde is, you're just turning this into a CH2OH. Everything else stays the same. Okay. We call this an alditol. Okay, that's an alditol. The one you got to be careful for is the ketose. And why do I have to be careful for that? Because it's very tempting, right? The aldose only has one answer, right? So it's very tempting to just do the same thing with here. I know if I were you guys on a time stress, I think I would just accidentally only put this one here because that's the way that the O is facing. But actually, you can't control which epimer you get. You're actually going to get a mixture of epimers. So you'll get both of these. Okay. Now, there is a way to convey this, so it can save you some time. The way that you can convey this very quickly is you can put a squiggly line through the OH and the H of the center you're making. If you do this, you're conveying to your grader that you're making both epimers. Okay. You can also just draw both too if you're worried. If you have the time and you have the speed and you have the strength, because even my hands start to, I've never ever talked about this, but my hands cramp like crazy when I'm doing these videos because I'm just constantly writing, constantly going through all of these. If you have that power, then you can go ahead and draw both, but you can also just use a squiggly line that indicates both epimers. Okay, cool. All right. But with that being said, that should be all the reduction reactions you should need to know. I know that on the 8 level, you guys cover less, just for because you guys are doing so much in a quarter, right? So don't stress too much. I'm pretty sure that's all of it. Let me just quickly check. Again, shout out. It is really helpful for me because I don't want to talk about things that you don't need to know. I don't want to stress you guys. I know I've done that a couple of times, so I apologize, where I've talked about something unnecessary and it stressed you guys out. So my bad on that. So let's see. So we got the bromine water, Oh, okay, my bad. Looks like you guys didn't talk about base epimerization. I apologize. I will make a note of that. I will send saying to Discord, you can maybe skip that part. If you don't want to go over that. We've got the aldonic, the alderic. Cool. All right, nice. And we got the alditol stuff. Nice. Okay, cool. So all that's left then for linear transformations is going to be building and breaking sugars. So the Kegliani fissure and the rough degradation. So Kegliani fissure KF synthesis. Again, this is just taking a sugar and building it up by one piece. The way this works is pretty simple. I'll just again just show from a generic sugar, just the part that matters. Okay. But this process, how it works is you add cyanide. Very quite often what you'll see for these kind of predictive products is you're asked to draw like every step just so she can track that you understand what's going on. Whenever you add cyanide to a CHO, you're going to flatten out that carbon. Okay. And this is what I would do. I would just add CN at the top, and then you want an OH and H like that. Again, just like with the alditol reactions, we can't control for which epimer we get. So we're actually going to make two. So right off in the first step, we lose complete control over which sugar we're going to make. We always make a mixture. So Kegliani fissure will always make a mix. You should always have two answers for Kegliani fissure. Okay. So again, you just want to turn this CHO into a flat line, and on the top just put a CN and then OH, just like that. Okay. From here we do a mild reduction, H2 usually, and Ba2SO4 quinoline. I don't think you need to know all of this. You just need to know that as long as you get, I think that H2PD with the barium sulfate and the quinoline, I don't think you need the quinoline part, but it'll be fine. The point here is that you're going to make specifically, right? The CN is a triple bond, right? This here is a triple bond. What we're specifically making with this triple bond is a double bond. So that's the imine. Okay, so we form the imine there. Again, I'm going to be a little lazy here, but that's okay because we're allowed to do this. We can make a squiggly line, right, to say that both epimers exist here. Okay. And then this imine, remember, imines are derivatives of carbonyls. So if you hydrolyze a derivative of a carbonyl, you turn it back into its carbonyl. So from this, what I get are two sugars, okay, both of them being aldoses. Right, cool. So Kegliani fissure synthesis is fairly simple, right? You add cyanide, you slightly reduce it, and then you just hydrolyze back into the aldehyde. Okay. Now, if I were to just kind of predict, like if I were just predicting a product, how can I do this really fast on a piece of paper? It's fairly simple. Again, we can use the squiggly line to our advantage here, right? Very, very simple to recognize. Cyanide, H2PD, and then Ba2SO4, and then H plus H2O. I remember someone said my handwriting is really bad, and I said I would lie for 2 hours. Imagine if that's what I was doing right now, just lying for 2 hours. That'd be crazy, wouldn't it? Wouldn't it? Right? Wouldn't it? Anyways, how can I predict this product very quickly? Again, the CHO turns into a flat line or a squiggly line, actually, and then you can put OH and H on either side. On top, I would just put the new aldehyde. Okay, so you're essentially implanting a new stereocenter in between right here. That's what you're doing. You're implanting a new stereocenter right there. Okay, so again, CHO we turned into flat. So if I have everything out right here, and I have the CHO here, don't forget your H's like me. I'm just lazy. I get rid of CHO, that becomes a squiggly line, right? OH and H, and then on top of all that, just another CHO. Okay. So for aldoses, this works perfectly. It just linearly increases. The amount of times you do it, just a linear increase. That's how these reactions work. Ketoses are a little tricky though. On a ketose, right, it might be, actually, maybe what'll help is if I draw the aldose like this, and then it'll make sense how we can do this reaction. So let's do it on this real quick. So let's say that I did the Kegliani fissure on this. So CN minus, H2PD, Ba2SO4, and then H plus H2O, right? To help you guys kind of visualize how this works on a ketose, let's do it on this one first. So again, this is going to stay the same, right? So let me actually just draw all of it out. So we have this here. How can I change this to make this correct? I just kind of get rid of that carbonyl. I replace it with a squiggly. right, turn into OHH and then the CHO, right? So, I mean, essentially, a way to think about it is all you're really doing to get this correct is you're replacing the carbonyl with OH and CHO. Okay, that's basically what you're doing. You're replacing the carbonyl. You can see that where we replace the carbonyl with a squiggly and CHO and OH. So if I take this and I just do this on a ketos, it's exactly the same thing. It just looks weird, right? You're just essentially same thing. All you're doing is replacing the carbonyl. So let's get all this down first. Right, we have a carbonyl here. All you're doing is replacing carbonyl with a squiggly and OH and CHO. There you go. So it just looks weird. It just looks kind of weird, right? It doesn't make sense why things are where they are. But they are there. So you just got to have them there. Okay. So that's how we can do that if you get a ketose. So it's not that ketoses don't work. They just don't linearly transform, right? And usually sugars, I mean, in nature, sugars linearly transform. Ketoses don't really do that, right? They're kind of weird. So that's just how that works. Okay. Cool. So that's a Achilles-Fissure synthesis, just linearly, increases sugar. Rough degradation is just the opposite of that. Only works on aldoses. And, why is it that we know that it only works on aldoses? It's because, actually, I should put 2 here. Yeah, let's just put 2. It'll make sense in a second why it's easier to see this with 2. Right. But the reason why this only works on aldoses is because of this first step. We use bromine water. And we just talked about that. Bromine water only works on aldoses. It doesn't work on a ketose. Okay. We use this. And then we use iron and peroxide. Okay. What does this do? This does a radical type reaction. I don't think you need to know the mechanism, but essentially what it does is it pulls off this hydrogen here. Okay. And then this molecule basically breaks down. This leaves as a CO2. So we call this a oxidative decarboxylation. And what we're left with is going to be those 2 OHs that we had before and a radical on this carbon here. Okay. Now, this radical itself will essentially just quench itself. It'll just turn into an aldehyde. Okay. So what we get out of this is going to be a sugar with 1 less carbon. Okay. So if I kind of just want to look at how to predict this very quickly, I don't think you need to know the mechanism for this one. This one's a bit difficult. It's a bit up there. Okay. But if I do rough degradation, so I see the Br2, and then the Fe3 plus or 2 plus usually, I think, H2O2. Essentially what you're doing, in a way, right, when we draw the answer to this, you guys will probably notice we're kind of wiping out a lot, right? I mean, we're definitely getting rid of this here, that aldehyde there, and then we're kind of getting rid of this guy here. So those top 2 carbons we're kind of getting rid of and replacing all of it with an aldehyde. Okay. It's not that we got rid of that second, that C2 carbon. It's just that it oxidized into that, right? So it should have 1 less carbon. Okay. Cool. Okay, so that's a rough degradation. Cool. So Achilles-Fissure builds up sugars and rough degradation breaks them down. That's how those reactions work. Okay. Cool. All right. Now, with that being said, that is all of our linear form reactions. Again, these are the 1% of reactions that take place when we have a cyclic hemiacetal. But let's go ahead and let's finish this off. Technically, I only have 10 more minutes, but definitely not finishing in 10 minutes, so I apologize. Try to finish this in 20. Looks like I'm actually not exactly where I wanted to be. Cool. Anyways, let's go ahead and look at the 99% of the time, the cyclic type reactions. So again, remember a sugar, regardless of whether it's ketose or aldose, right, will spend a majority of its time in cyclic form. Right? And so there are certain reactions that we can do in cyclic form that take advantage of the inherent reactivity of this hemiacetal carbon or this anomeric carbon here. Okay. So again, we talked about how to cyclize these. Hopefully that's not too bad. And maybe you watch the other video if you need extra support on that. Okay. But now when we look at this here, right, this hemiacetal carbon is particularly special. So special that if we were to do reactions in acid, right, so again, let's say that I have this here. Again, you might remember alcohol reactions, they like to go through, when we put them in acid, we like to go through cations. So if I were to put this in a particular acid, right, a particular temperature, usually low, and I were to guess which of these alcohols, were to react with the acid first, right, I could kind of think about, where on this sugar the cation would be the happiest. So all these positions here, right, I could think about cations being on those positions. I think maybe the worst position is this one because that's primary, so I won't even consider that. But the rest of these are secondary. So maybe we don't care. Maybe all cations can form. Maybe if I draw this in, you guys have an idea, right? I think that out of all these cations, the best one is the one that originates from the anomeric carbon, because that anomeric carbon has that neighboring support by the lone pair if that cation were to form. Okay. So if you do a reaction in acid, the anomeric position is the one that always protonates, right? That alcohol always protonates into water. And when we form water, what do we want to do? We want it to leave. Again, I mentioned at the beginning of the quarter, we form water, it leaves. We're always going to do that. And we're doing it at the end of the quarter now too, okay? So we form that water. And what we get out is a sort of internal carbonyl-like structure, right? This weird, like internal carbonyl, right? And all these other alcohols kind of stay the same. Okay. Now, depending on what's in solution, right, that thing can capture on this cation or on this carbonyl type structure, usually some kind of alcohol molecule. So maybe I'll do like a ethanol or something. But that ethanol can go ahead and capture. But what we get out of this is going to be this structure here. Okay. Now, first off, because this structure here is planar, it's a double bond, it's planar. Remember, back in those alkene reactions, when the cation could be attacked, when the cation could be attacked, or when the proton could attack the alkene could attack the proton, right? We don't actually know what face the alcohol attacks from, right? Because of this planar structure. This here is planar. Okay. So not only do I get the alpha anomer, but I also get the beta anomer as well, right? I have no idea. Maybe there's an inherent, preference. I won't know. I absolutely do not know. Okay. At least you guys don't know either. So I get two anomers out of this reaction, the alpha anomer and the beta anomer. Okay. So in acid, right? Again, remember that AAA thing, right? Acid anomeric, right? I guess scramble, right? That's not, I guess it's not AAA, but acid anomeric is what you want to think. And then we scramble, we get both alpha and beta anomers on that. Okay? The other thing is that when I look at this carbon now, right, this carbon here, that carbon doesn't have an OH anymore. So if this were like, let's say this were an aldose, right? Then there would be an H here. That's fine. If this were a ketos, it'd be a CH2OH, right? Okay, that's fine as well. But there is no OH originating out of that carbon, right? This is no longer a hemiacetal. This is now an acetal. And so when we have cyclic acetals, right, we call these glycosides. And glycosides absolutely do not equilibrate with their linear form. Absolutely not. There's no equilibration, right? They are locked sugars. So what do you think about them? They are locked sugars. And so if these guys are locked sugars, these guys don't have the capability of turning into their linears. Well, hey, looks like all that stuff we talked about the last 40 minutes, all those reactions, looks like they were moot. At least they're moot when we have glycosides. Okay. So acetal sugars are known as non-reducing sugars. And these guys will not respond to any of those Tollens or Felons tests or any oxidation test at HAP. Okay. There is one exception. There is one exception. Technically, HNO3 could oxidize this guy out here, but we're not oxidizing a carbonyl, so it's still not a reducing sugar, right? The whole point of reducing sugars is that the carbonyl is what's oxidized. Okay. So if you're ever asked a question of what is a reducing or non-reducing sugar, you're looking for acetals for non-reducing, and you're looking for hemiacetals for reducing. So look for these carbons here where we have two oxygens sort of flanking them, right? These anomeric positions, right? That's how you figure out, oh, that is a, reducing or non-reducing. That's a hemiacetal acetal. Okay, cool. All right. So we can make glycosides. Again, in acid, because we have this sort of scrambling of information, we get both anomers. So just to kind of summarize that on this page here, just with some random sugar, who cares where it's at, right? Right. If I do this in like H2SO4 and let's say methanol, right? Again, we're an acid, so think anomeric. So I will make 2 sugars. Again, we can use a squiggly line. Squiggly line indicates that we don't know which anomer forms, just like with sugars, we don't know which epimer forms. But that's the only position that will react. Okay, everything else stays the same. Okay, then we get our glycoside. So then what happens in base? What if I do base? So let's say I do NaOH and I do CH3I. Right, you guys think it's like completely opposite? You guys think it's completely the same? Well, the nice thing here is that, I mean, base is the complete opposite of acid. So we observe actually the complete opposite on everything. First thing we completely observe as opposite is that instead of having only the anomeric react, we have every single alcohol react. So NaOH will deprotonate every single position. Okay. And every single position then will be methylated. Okay. So we get a completely methylated glycoside. The other thing is that because we don't form a cation in base, we have absolute control over our epimer, or sorry, over our ionomer. So here where we get 50% alpha beta, this that started 100% alpha stays 100% alpha at the end of the reaction. Kind of sweet. Right? Base will completely keep that there. Okay. So in base, everything reacts. We keep our anomer. In acid, only anomeric reacts and we get both anomers. Okay. Now to make sure you guys are paying attention, let's say I did H plus H2O. We're an acid, so who reacts? Again, acid only reacts to anomeric, so everything else should stay the same. And then again, I mean, we're basically the Nuga is water, so we're switching the OCH3 with OH. Again, I have no control over the anomer. I'm going to get 50% alpha, 50% beta. Okay. Cool. So those are the glycosidic reactions, or the reactions of how to form glycosides. Okay. And sort of the difference between having a acid and basic condition. Cool. Now, with all that left, I think all that's left now in terms of reactions should only really be, what's left? I think the only thing left now, I don't think there's actually any reactions. I think all that's left now is just the disaccharide stuff. So this alcohol stuff, the alcohol can really be anything, right? I made it methanol and I made it here ethanol, but if you think about it, another sugar could be an alcohol too. So, when your body is making, disaccharides, polysaccharides, or a plant is making them, right? Really what they're doing is they're doing the same process, right? But they're just doing it with the alcohol of another sugar. So I could take 2 of these guys and kind of combine them, and that would make a disaccharide. Right. So, for example, I can make this here. This is gonna be kind of hard to draw. There we go. Okay, so this could be a disaccharide here. Okay. And I know there's a couple disaccharides you need to know. I'm going to leave that to your notes for you guys to figure that out. Just have them on your note card or whatever. Okay. But a disaccharide is just the combination of 2 of these sugars. And so there is usually a bit of nomenclature that goes around on how to figure out how to name these. The linkage, so the link between your two saccharides, your two sugars, is usually named alpha or beta based on the anomeric position of the sugar that's using its anomeric. So these guys are bonding through here. So technically they're bonding through these two carbons. And the anomeric carbon is the one that determines whether it's alpha or beta. In this case, right, this one's the anomeric. This is not anomeric. So this here is anomeric. It's pointing down, so it's alpha. So this would be an alpha linkage. Okay. You can even describe the position at which you're bonding it. Again, just counting just numbers. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and then 6. So this would be a 1,6 alpha linkage because you're bonding through the alpha, the anomeric 1 carbon and the 6 carbon of the other sugar. Right? That's the bondage there. Okay. For sugars that bond through both anomerics, you could, if both of them are different, then you can label them different. So for like example, if I had an example where a sugar was bonding like alpha and beta, like I'm trying to show in this example, but I'm doing a really bad example, doing a very bad job of showing it. Yeah, actually, let's do this. So let's say that I had this here where this is pointing up, so it's beta, and this is pointing down, so it's alpha. You would just call this an alpha beta linkage and then just number it, right? So this would be 1, 1, 1, 1, right? Alpha beta linkage. The one where you have to be careful for is ketoses, because ketoses are a bit sneaky. The C1 of a ketose is actually the CH2OH. So let's say that I have this here. Right, this here. Again, the anomeric position is this one. So we would call this an alpha, so this pointing down. So this would be an alpha linkage. But when I do the numbering, again, this one is obvious, 1, 2, 3, 4, 5, and then I guess 6 or whatever, but this would be 3. So we're bonding through 3 here. So we're bonding through 3. But for this guy here, because we have the CH2OH, the ketose actually, this is number 1. This would be 2, 3, 4, 5, 6. So this is actually a 2-3 linkage. So ketoses are, just watch out for those. Those are the tricky ones in the linkage game. Let me actually check the notes real quick. Let me see if there was any particular ones you talked about. Looking through this, I don't see. Okay, yeah, it looks like, I mean, she looks like she talked about 4 of them in particular. She looks like you talked about disaccharides. So just, I mean, just be aware of those. But yeah, just know those rules. I think you guys will be fine. These are usually not too bad. This is, I think once someone does it in front of you, it kind of makes sense. So you shouldn't worry too much. Okay. The last thing I'll leave you guys on this is just the idea of reducing and non-reducing with disaccharides. Very simple, right? If there is a hemiacetal, it's reducing. If it's acetal, it's non-reducing. So in this case, here, this here is completely acetal, but this has a hemiacetal. So this would be counting, this would be a reducing disaccharide. Same thing with this one, right? There's hemiacetal, so it's reducing. Both of these anomerics are acetals, so this is non-reducing. Okay, cool. All right. So with that, I think that's what I'm going to call it for this one. I didn't want this one to be too long, and I trust your notes to do like all the bio stuff that I can't really cover because I'm not bio. Let me just one quick look through this again. Thanks a lot to the person who sent me notes. It really helps. Oh, my bad. It looks like oops. I guess you don't need to know wolf degradation either. I apologize. I did not know that. Okay, my bad. My bad. Cool. All right. But anyways, yeah, looks like we got everything. So cool. All right. As always, just let me know if you have any questions. Guys, have a great rest of your night.